Welcome to the Math Record. Today we'll be covering Euler's method for approximation. This video will cover part 6 of chapter 2. Okay, let's begin. So what is Euler's method? Right? So Euler's method is basically just a way to find really close approximation for graphs. So this is just a disclaimer. So this video will be different from our previous derivative videos. While the other teaches the basic of derivatives, like the actual basics and the rules, like inverse derivatives and basically implicit derivatives, this video will be more of a practical sense where we're going to be using a derivatives to find really close approximations. Okay, so onto Euler's method. The main point for this method is basically just to find coordinate points. This is all it does basically. So imagine having to find the coordinates of a graph using only the graph's really small changes. So what does that mean? Well, basically, let's say we have a graph. I'm just gonna draw it super big. So let's say we have a graph like this, right? Let's say we use some kind of really simple graph. And let's say we are given a point right here, okay? So we're given this point. And using this point, they want to say what is this point right here, right? So instead of giving you the graph, well, let's say our graph is f of x, right? Let's say they didn't give you this graph, right? Instead, they gave you the derivative of this graph, which is called derivative of x. So they're giving you really small changes of how this works. So remember what our definition for derivative is? It's basically just small changes in a graph. Well, it's kind of defined as a slope also, but imagine, right? Let's use a different color. Imagine we have a point right here, and we take the slope of it. And then we take another point right here, take a slope of that, take a point right here, take a slope of that, right? So if we have all these slopes together, right? If we add all these slopes together and plus this value, we could get this value. So why does that work? Well, basically, these slopes are just really small changes in the graph. So if we add all these small changes between these 2 points, then basically we could just find the change between these points, like this curve right here, and then we could actually get this point from this point. And that's the basic idea for Euler's method. So as you see, I drew 3 dots. When you're using Euler's method, there are a set amount of dots you can make, which is basically called the step size. So imagine how precise you would be of having 3 dots, right? Let's say 3 dots right here, right? And they're all equally spaced versus having 4 dots, one right here, one right here, one right here, and one right here, and they're all equally spaced. Well, you could say that it's basically more precise, right? For the 4 dots, because if you have 4 dots, that means you're accounting for even smaller changes, and you're accounting for smaller changes, but you're also accounting for more, basically more dots, right? So you're accounting for more data, but also you're accounting for even smaller changes. Then you're becoming even more precise. So as you increase the dots there are between these graphs, right? Right? So let's say you have like a bunch of these dots in here. Then basically we can find all the slopes of these dots, right? And then we can add all these slopes together and then add the y value of this point, and then we could basically get the y value at this point. And that's basically how Euler's method works. So how do we know how many dots we had to use? Well, basically Euler's method doesn't know either. So what I mean for this is basically you could choose your own. Usually if you're working in a classroom and you're learning calculus, or if you're doing the AP exam or how it works, or any exams that use this idea, they're either gonna give you one or you could use your own. So how you're gonna choose the amount of dots is often referred to as the step size. Right? So the step size, let's say you want to start from 0, x is equal to 0, but you want to find when x is equal to 9, right? Well, basically, let's say we have a step size of 3. Then basically you go from 0 to 3 to 6, then to 9. You see how that works, right? Because it's 0 plus 3 is 3, 3 plus 3 is 6, 6 plus 3 is 9. And that's why this works, because then we could basically tell how many dots we have, right? Because if we have a graph like this, then basically we just have our initial point is at x is equal to 0, then we find a point at x equals to 3, and then another point at x is equal to 6, and then we can find the point when x is equal to 9, right? So we're adding to this change and this change, then we can finally get this number, right? So we have a point here, add the change from to this point, right? From this point right here to this point right here, and then from that change, we get at this change, and then we can finally get this point. And that's basically how we do it. And that's basically what we're going to use, step size. So there isn't a general method of choosing step size or which one's the best, what's the best number for step size. Usually you just choose your own. The general idea is that if you have a smaller step size, you have more precise measures, right? So let's say you have a step size of 1, where you're basically going from 0 to 1 to 2 to 3, to 3 to 4, and then to 5, then to 6, then to 7, then to 8, and then to 9, right? Because you want to get x is equal to 9. So now you have 1, 2, 3, 4, 5, 6, 7, 8. 8 points between x is equal to 0 and x is equal to 9. So you're going to have to find when. So this is basically just x equal to 1, x equal to 2. So you're going to find all these values at these points, and then add those changes from 0, and then to get to 9. And that's basically what we're going to do. So what is the way to do it? Well, basically, I'll just show you with the example. It's easier to learn with the example, and then you could just basically follow the same process. It's basically the same way for every single equation, but it's generally you just gotta make a table, and you're gonna follow this table. So once you get used to it, it just seems very tedious because you're doing the exact same method over and over again. So what I mean is basically, let's just say we have a graph like y is equal to x squared, right? Let's say it's the derivative graph. Sorry about that. The derivative of y is equal to x squared, right? And let's say we're given the initial point that at x is equal to 0, we're at 1, okay? And we want to find when x is equal to 2 using a step size. Our step size is usually referred to with an n, or how I usually refer to it. Let's say our step size is 0.5, okay? So our 0.5 is our step size. And then what you do is you basically make a table. Sorry about this. Kind of not line. Okay. And then we're going to make another right here. And then we make these columns. Okay. Your first column is going to be your x. Your second column is going to be your y. Your third column, I usually like to write as n, so I don't forget it's n. But if you don't want to, you don't have to. It's not that important. You just got to know your n is 0.5 for the example. Your step size is not always 0.5, but I'm just using 0.5 as the example. So whatever number is more convenient for you, just use it. Usually I choose step size as basically the amount of points I want. So basically I have 0 to 2, right? X is equal to 2. Well, basically I see that 2 minus 0 is 2, right? So I want to choose a multiple of 2 so that it adds up evenly. So let's say we could choose 1, right? So a step size of 1 would be 0 to 1 to 2, right? So we only have 1 point. That doesn't seem really precise at all, right? So let's just choose something else. So remember, our difference was 2 minus 0 is 2. So what other number can we choose instead of 1? Well, we choose 0.5, right? So if we have 0.5, we have 0 to 0.5, 0.5 to 1, and then 1 to 1.5, and then 1.5 to 2, right? So you're just adding 0.5. The difference is 0.5, and that's why it works, because we're using multiples of it. So if you're using 3, right, then basically we just go from 0 to 0.5 to 1 to 1.5 to 2 to 2.5, then to 3. So usually I like to use at least like 2 to 3 like data points. It doesn't matter like what the step size is. It's just that if you're using a smaller step size, you're generally gonna have a better approximation. And that's what I like to use. So usually for these kind of numbers, I kind of use 0.5. So after your step size, you're going to put your derivative. So after your derivative, you're going to have your step size times your derivative. So it's your n times your derivative of y. And that's the reason why I like to include this n, because then I just know what to multiply by. But usually it's going to stay the same because all this n is just going to be 0.5. But like in case you make a math mistake and you accidentally multiply by 0.4, you can see where your mistake came from. So basically, after that, we have this. All this space is basically just going to be your y plus your n times y times the derivative of y, basically. So I'm trying to make this a little bit more precise. Times your derivative of y. Okay. So it's going to be this value plus this value is basically this final column. So why do I do that? Well, basically, x and y is going to keep track of what your coordinates are. Your n is going to keep track of your sample size, your step size, I mean. Your derivative of y, this is going to change. Your derivative is going to change because your x is going to change, right? And then you're going to have your change in your really small changes, which is n times derivative of y. So these are also going to change because n is going to change. I mean, your derivative of y is going to change, so this is going to change. And then you're going to add that new value. And this new value is going to become your new y value. So let's use our example for now. So we're going to start, we always start out with our first point. So our first point they gave us is 0, 1. Okay? So we have 0, 1. So what's our step size? 0.5. So what's our derivative at y? So our derivative is equal to x to the power 2. So what is x? Well, our x is right here. X is 0. So we plug in 0 in here. So 0 squared is just 0. So n times y, so it's basically just this times this, which is basically 0.5 times 0, which is just 0, right? Now it's just y plus n times the derivative of y. So it's basically this number, which is 1, plus this number, so which is 0. So 1 plus 0 is 1. And that's basically going to become our new y. Okay, so that's going to finish one row. And now we're going to use our next one. So what is our next x value? Well, we said our step size is going to go by 0.5, right? So 0 plus 0.5 is just 0.5. So this is our second step size. So this is going to be our second point. It's that x is 0.5, and our y value is going to be at 1. So how do I know it's 1? Well, basically, Euler's method tells us that this value is just going to become this, right? So basically, that's why it's going to be like a sequence, and why it's really tedious, because you're going to use your old values to find your new values. So if you're going to do all the math here, and then you get this you get some kind of value over here, right? You're going to put this value as your new y value for 1, when x is equal to 1. And you're just going to keep doing that over and over again until you get when x is equal to 2. Okay, so our step size is 0.5, right? It's always going to be 0.5. This column is usually going to stay the same anyways. But I wrote n just so you could keep track of where the 0.5 is. And then our derivative at y, our derivative is not 0 anymore because x is not 0. X is 0.5 now. So now we put 0.5 squared. So 0.5 times 0.5 is 0.25. About that, 25. Now n times the derivative of y, so 0.5 times 0.25 is 0.125. If you want to round it to 0.13, that's fine. But usually I like to keep like 3 decimal places. Keeping 2 is fine. Just don't keep 1 decimal place because then you're gonna like sometimes change the number by a lot. So usually I like to keep to 3 or 4 decimal places, which is pretty good. So anything higher than that, you could basically just round. So you have like 0.371254, right? I'm just making up random numbers. So basically, if we have, we need to write that for. Well, basically, I only want to keep this number, right? So basically, we're just going to use the rounding rules, so 3.71, right? So we're just going to write that down. Because 2 is lower than 5, so we're just going to round down to 0.375. I mean 371. So if there's too much decimals, basically just kind of use common sense and just kind of round to like a really close number, which is fine. So it's easier for the calculations. But round to a reasonable number. We don't want to round this to like 0.1, because then you're missing the 0.025, because that's a really important. That seems really important because while this is small, this is like 0.025 is like it's not small enough compared to 0.1. So then you might want to include it because it might be very significant later. If you want to be more precise, basically just keep all the digits if you want, and basically just do this all in your calculator. But if you want to do it by hand, you basically just round. So back to Euler's method, right? So your y, which is 1, plus your your step size times derivative of y, which is basically 0.125, is equal to 1.125. So now that completes your column, so you're going to make the next one. So your next step size, you're going to add 0.5. So 0.5 times 0.5 is 1. You see how that works? From 0 to 0.5, now to 1. So basically, your next one is going to be at, right? So what's going to be the next one? Well, it's going to be 1.5, right? And then after that, we have 2, which is what we're going to look for, because when x is equal to 2. So we're basically looking for this. Now, what's our y value for when x equals 1? Well, it's equal to 1.125. Okay? So basically, now we're going to find our n is 0.5, always. Now, what's our derivative of y? It's at x squared, right? Our x now is 1, so now it's just 1 squared, which is 1. So our n times derivative of y, so it's 0.5 times 1 is 0.5. So y, which is 1.125, plus our n times y, which is 0.5. So we get 1.625, right? So that's our value. And now this becomes our new y value. So we're basically just repeating these like sequence over and over again, right? So this one became this one, this 1.125 became this 1.125, and this 1.625 became this 1.625. So we're just doing this over and over again, and then we're basically finding the value. So when x is equal to 1.5, it's around 1.625. It's not precisely at 1.625, but it's really, really close to 1.625. So that's basically what the Euler's Euler's method is saying. But we're not looking for 1.5, right? We're looking for 2. So we have to do this one more time. So 1.625, we have 0.5. So the derivative of y as x, so 1.5 now. So 1.5 squared is equal to 2.25. Now n times y, which is 0.5 times 2.25, is equal to 1.125. As we did over again, the original y, right? So 1.625 plus our n, our sample size, our step size times our derivative, which is 1.125, which is equal to, let me make this smaller so that we can fit it. So this number plus 1.625 is equal to 2.75. And now we're basically done. Well, basically, you're probably asking right now, how are we done? We still have to do 2. Well, basically, we don't. So, as I said before, right, we're using our previous number, and that becomes our new y, right? So this one became this one. This 1.125 became this 1.125. This 1.625 became this 1.625. So this 2.75 became right here is 2.75, right? Because now you already found the coordinate. X, when x is equal to 2, y is 2.75. Well, don't we have to do it so we can find the y plus n times the derivative of y? So we have to find a new number here. Well, basically, no. This new number tells us what is the value, what's the y value for the next x value. So this x, this value, will find out when x is equal to 2.5, not when this value is equal to, not when x is equal to 2. So it's gonna be different. So if you're gonna have to do all these math, be sure not to get tricked by that idea that you have to do one more row, right? So you don't have to do that. When you basically end at the number that's the step size that's before that number that you want. So we're ending at 1.5, which is the thing that we end before 2. That's gonna become your answer. So our answer is just it's 2.75. Right? So that's our answer. So when x is equal to 2, our y value is 2.75. So basically, since I already used a really easy derivative, let's kind of check if that's right. Okay? So let's say our derivative was equal to x to the power 2, right? I'm not going to explain how we could get it. It's basically the original equation is x to the power 3. Okay? So how do I know that? Well, basically, it's just 1/3. Well, if you keep track of our derivative rules, right? We just bring our, if we have something on the front, we could just take it out. And then we basically just do the derivative of this, right? So basically, the derivative of x to the power 3, as I always say, bring the exponent down and then subtract 1. So the exponent down is 3, subtract 1 is 2. So the derivative of x to the power 3 is 3x squared. So 1/3 times 3 is just 1, right? So that just leaves the x squared. This is the same thing, right? X squared is equal to x squared. This is the derivative, right? So basically, it's the same idea. So this is our original equation. So this is true. So let's say we wanted to find when what's the y value when x is equal to 2, right? So we want to find this value. Well, basically, using our Euler's method and our derivative of y, we found out that y is around. I'll use squiggly lines. This means approximate is about 2.75, right? Well, let's find the real value. When x is equal to 2, is 1/3 times 2 to the power 3. That's a third. Sorry. Well, it's just 8 to the power. It's just 8 divided by 3, right? 8 divided by 3 is around like 2.6 repeating, right? You see how close that is? Because this 2.6 repeating is just like this, right? So it has infinite sixes. You see how close that is? 2.75 to 2.6? Because that's basically the idea of using Euler's method. It uses like really small changes to get really, really close numbers. Now, that's when we use a step size of n is equal to 0.5, right? Imagine using a step size of n is equal to 0.1. Then we get even more points, and then we get even smaller changes. So since we have more points, we get more precise. And so as we have smaller changes, it gets even more precise because we're doing smaller changes, and then the smaller changes make less mistakes, basically. Because if you're using like higher numbers, it's more likely to make bigger mistakes. So that's like a logical way of reasoning it. But basically, if you use that method, it seems very, very tedious, but basically it's going to and using this chart, basically you're going to get the answer. So what you always do as a refresher, you have your derivative of your equation, your original point, your point that you want to find, which is x equal to 2, and your step size. And then you could just make this chart. The x value, the y value, your sample size, your derivative, your not your sample size, your step size times your derivative, and your y value plus your step size times your derivative, right? And you basically just follow this equation. So you basically follow these equations. You have 0, 1 as your first. Get your new y value. That becomes your new y value for your new point. And your new point is basically just adding 0.5 to every single like value as it goes on. And that's basically how you find it. you kind of just follow this entire table. If you want to screenshot this to see how it works or just take notes, it's fine. But basically, this is just a general idea of how it works. Okay. And we have one last note to conclude this. Usually when they have the derivative of y, let's say, right? Instead of saying x squared, if they want to be more complicated, they could put like x squared plus y. So it's going to be like an implicit differentiation, which I covered in a previous video. Basically, the idea is that, let's say you start at 0, 1, right? Which is what we did. Instead of saying our previous value, which we said our previous derivative was 0, right? Because we didn't have this, so 0, here is 0. Well, basically, now our derivative is changing. So we put a derivative x here, and then put a y here. So 0 squared plus 1 is just 0 plus 1 is just 1, right? So be sure to keep track of what your derivative is, and then you basically just plug your values in. So it doesn't matter how the derivative is set up. Basically, all you care about is plugging in your values for x and y, if there even is a y, basically. Or if there even is x. Because sometimes the derivative could be equal to just like y cubed or something. Or your derivative is equal to x times y. That be sure to keep track of what it is. You just follow the chart and basically you're going to be fine. And that basically covers everything for the Euler's method. Thanks for watching, and I'll see you at the next math record.